So, hello everyone. Today I am going to discuss a new topic, that is metabolic energetics. This is the part of module 2. So, first let us revisit what we discussed in the last lecture. So, we discussed stoichiometry of cell growth as well as the same for the product formation, and for the stoichiometry equation, earlier we discussed to balance using this carbon balance, hydrogen balance, nitrogen balance, oxygen balance and respiratory equation. Next study what we discussed was based on the degree of reduction and yield coefficient Y. If these two parameters are known to us, still we can go for the material balance. So, based on degree of reduction and yield coefficient, we perform the elemental balance, and further we discuss the stoichiometry of the product formation. So, there are different classes of the product formation, like class 1 where product is directly part of stoichiometry relation, and class 2 where products are indirectly related with stoichiometric equation. So, in this case the degree of reduction of the product is the part of stoichiometry relation. Now, for today's lecture, what we are going to discuss, first the metabolisms, and next we will see the concept of energy in the living system, and what about the energy efficiency. So, metabolism, as we know, the living system, we can consider living system as a complex chemical reactor where more than 1000 independent biochemical reactions which are enzyme catalyzed are ongoing to perform various functions like degradation of nutrients, biosynthesis of small molecule and biosynthesis of large macromolecules. And this total of all chemical reaction activity in the cell is called metabolism. And if you see these metabolic reactions, they are organized in the form of pathway, and those pathways are circular and closed pathways. Now, to understand this, what is the source of energy which living system is utilizing? So, it is classified two kinds. One is maybe chemical, other is the light, that is the source of energy. So, where chemical is a source of energy, that is called chemotrophs, and in the case light is the source of energy, that is called phototrophs. Further, in the chemical sources, it can be lithotroph, inorganic, and organotroph, organic substrates. And what is the settling molecule for energy is the ATP. So, once we are taking the energy, so that need to be converted to the work. So, what are the work being done? First is chemical synthesis of large and complex molecules for the growth, transport of ionic and neutral substrate, it may be against concentration gradient, and mechanical work required for cell division and motion. So, these are the work, and if you see all these works are energy intensive, it requires the energy. So, they are non-spontaneous. To make them spontaneous, these processes are coupled with hydrolysis of ATP, where energy is released to make this non-spontaneous process to spontaneous process, to make the value of delta G negative. Now, as we know, these are the four major sources: carbon, nitrogen, sulfur and phosphorus. So, as I told, for the carbon, if someone can take carbon dioxide or other compounds starting from sugar, proteins and fat. There will be nitrogen source, sulfur source and phosphorus source. So, based on the carbon source, again we can classify. If carbon source is CO2, this is called autotroph, and if it is chemicals, this is called heterotrophs. So, based on the energy source, we classified as chemotrophs and phototrophs, and based on the carbon source, we are classifying that heterotrophs and autotrophs. Now, we can combine these two. The chemical source, if it is organic compound, this is called chemotrophs. If it is carbon dioxide, that is called chemoautotroph. And if the energy source is the light and carbon source is the carbon dioxide, then this is called photoautotrophs. And if energy source is light, carbon source is organic compound, then it says photoheterotrophs. So, in this way we classify based on the requirement of carbon source and energy source. Now, as I told, when we perform the work, we require the energy, and energy is coming from the hydrolysis of ATP, and for the 1 mole of ATP, minus 7.3 kilocalorie energy is released. So, another interesting molecule is the NADH, which have the reducing power, and it participate in the oxidation reduction reactions. Oxidation reduction reactions. To understand this energy concept in the metabolism, I have taken one example of carbon catabolism. So, catabolism means we are breaking down the nutrient to get the energy. So, let us first see the simple EMP pathway. So, it says in case EMP pathways, glucose is converted to pyruvate. So, one molecule of glucose is converted to 2 molecule of pyruvate. In addition, there is generation of 2 ATP molecule and 2 NADH and H plus molecule. Further, this pyruvate is converted to lactate. So, pyruvate is converted to lactate, and if I combine these two equations 1 and 2, this is called overall glycolysis, where glucose is converted to lactic acid. So, it says glucose plus 2 pi plus 2 ADP, this is converted to 2 lactic acid molecule plus 2 ATP and 2 H2O. So, you just see gives free energy for this reaction is minus 32.4 kilocalorie per mole, but when glucose is directly converted to 2 lactic acid, delta G value is minus 47. So, there is a decrease in the delta G value, and what is that change? Change is 47 minus 32.4, this equals 14.6, and this 14.6 accounts for 2 ATP molecule. For 1 ATP molecule, it is 7.3 kilocalorie per mole. 7.3 into 2 is 14.6 kilocalorie per mole. So, what it says, in the case of carbonate catabolism, energy is stored in the form of ATP. And what is the apparent efficiency of free energy transfer? So, if we just see how much energy was conserved in the form of ATP was 14.6, how much was total energy? 47. So, it says 31% is the apparent efficiency of free energy transfer in the form of ATP. Further, next is the respiration. Respiration says this is an energy producing process where reactions take place in the presence of oxidant molecule, and when oxidant or oxygen, that is the aerobic process, and when oxidant other than oxygen is involved, the process is called anaerobic respiration, like sulfate, nitrate here. And these are various microbes which participate in this particular reactions. So, if you see TCA cycle, so in the case of TCA cycle, the pyruvate is entering and converted to carbon dioxide and ATP, FADH2 and NADH. So, one pyruvate molecule is generating 3 carbon dioxide, 1 ATP, 1 FADH2 and 4 NADH and H plus. So, we have already discussed in the case of oxidative phosphorylation, one FADH2 molecule give rise to 2 ATP molecule and one NADH molecule give rise to 3 ATP molecule. And in respiratory chain, hydrogen atoms are oxidized to the water, and ATP generation in this process is called oxidative phosphorylation. So, what happens, this FADH2 and NADH, they go for oxidative phosphorylation. Now, if we club this TCA cycle with EMP pathway, so in EMP pathway we had 2 molecule of pyruvate and 2 ATP molecule. So, 2 ATP is here, if I write here ATP, 2 molecules are here and 2 NADH. So, 1 NADH give rise to 3 ATP. So, now it has become 6 ATP from here. Now, 1 pyruvate molecule is giving rise to 1 ATP, FADH2 and 4 NADH. So, 2 pyruvate molecules is give rise to 2 ATP, 2 FADH2 and 1 FADH2 gives 2 ATP. So, this becomes 4 ATP molecules. Further, there are 4 NADPH and each NADPH gives 3 ATP. So, this has become 4 into 2 into 3, 24. So, total become 38 ATP molecules. So, you can see there is a overall glucose is converted to carbon dioxide and water along with 38 ATP molecules. Now, we can calculate the energy capture efficiency from glucose. If you oxidize it, you will get carbon dioxide plus water, delta G value is minus 686 kilocalorie per mole, and energy yield from the glucose in a respiring cell is 38 ATP molecule. 38 into minus 7.3, that becomes minus 277 kilocalorie per mole. So, what is the energy capture efficiency if you club this glycolysis and respiration? This is 40%, that is it. So, 40% is the energy capture efficiency when we are clubbing glycolysis and respiration. When it was only EMP pathway, the efficiency was 31%. Next example, we will see photosynthesis. This is called reverse of respiration. What was the equation for the respiration? If you remember, it was C6H12O6 plus 6O2, this is converted to the 6 CO2 plus 6H2. So, if I reverse this reaction, this is the same here, that is called photosynthesis. And once I am reversing this reaction, so this reaction was generating the energy, but if I am reversing, then this will be requiring the energy, and what is the source of energy is the light. So, here it requires the energy in the form of light, and so we can calculate the energy of one photon is equal to h c upon lambda. H is the Planck's constant, c is the velocity of light, and lambda is the wavelength. So, we know this Planck's constant and velocity of light. So, we can put these two value here. So, it comes out to be E equals to 2.859 into 10 to the power 4 divided by lambda in nanometer kilocalorie per mole. So, if you know what is the wavelength of light, you can calculate what is the energy of one photon. Now, in the photosynthesis, as I told, it requires the energy. So, let us see how much energy it is requiring. So, if you remember the photosynthesis system, it has the photosystem 1 and photosystem 2, and in photosystem 1 and photosystem 2, absorption of 2 light quanta by chlorophyll and other pigment results in the excitation of 1 electron. So, 1 electron requires 2 photons and 4 electrons are transferred to generate 1 oxygen molecule. So, for 1 oxygen molecules there are 4 electrons, for 1 electron there are 2 photons. So, I can say this for 1 O2 molecules it requires 8 photons. Now, if you go to this equation, this how many oxygen molecules are generated here? 6. So, how many photons will be required? This will be 6 into 8, 48 photons will be required, and let us assume the wavelength as 700 nanometer. So, energy of one photon will be 41 kilocalorie per mole. So, what is how much energy is required or how much energy is supplied for this reaction is 48 into 41, it is 1968 kilocalorie per mole. So, this much energy is supplied, and how much, what is the delta G value for this reaction is 686 kilocalorie per mole. So, how much, what is the efficiency of light absorbed is 686 coming from this reaction divided by how much energy is supplied for this reaction is 1968, this equals to 35%. So, why we are always seeing the lower efficiency? Because all the living systems are open system where the transfer of both mass and energy takes place. So, it might happen that in place of we are discussing one metabolite, there may be formation of other metabolites as well. Other options are the loss of energy to the environment, which we are not accounting here in this calculation. So, what we discussed is to understand the metabolism and see how it is linked with this energy efficiency. So, first we discussed the carbon catabolism. The efficiency of carbon catabolism was 31%. When we integrated this with glycolysis, the efficiency becomes 40% because we are able to generate 38 ATP molecules. Next example we discuss is the photosynthesis. Here we require the energy because we are going to synthesize the glucose molecule using this carbon dioxide and water, and how much energy is required for this synthesis is 48 photons, that is equals to the 1968 kilocalorie per mole. And what is this energy, free energy for this reaction is 686 kilocalorie per mole. So, the efficiency is 35%. So, in this way we can visualize what is the energy efficiency or the energetics of the biological system. So, I will stop here for this lecture. Thank you so much.